Hello, y'all. Welcome to my DB Chemistry curriculum. Today we're doing Lesson 50, Structure 2.2.12. This is an HL lesson. We'll be discussing benzene. It's an important example of a molecule that has resonance. So what we're going to mainly focus on is the structure of benzene based on physical and chemical evidence and kind of its discovery and how we led there. So let's get started with benzene, which as we stated above is C6H6, which at first is kind of a quite difficult molecule to draw. The general formula for things with carbon is for every one carbon, you have two times that many hydrogens plus two. That's what we would call carbon with single bonds. If you have double bonds, for every one carbon, you have twice as many hydrogens, and that's for each double bond would reduce the number by two, and triple bonds reduce it further. So benzene was kind of a weird molecule until we had a scientist named Kukele or something, or Kukule, and he discovered benzene or he proposed the idea for benzene to be a carbon ring with three double bonds. So this was the working theory for benzene. Now, the thing about that is that we notice that we have alternating double bonds and then we have these areas of single bonds. So from what we learned in our previous lesson about resonance, you could probably deduce that these bonds could be rotated and we would have the same molecule, but these would be resonant structures. However, we didn't actually know this at the time of discovery. So we were able to start collecting physical and chemical evidence that kind of helped us learn a little bit more about it. And this is what the DP chemistry curriculum wants you to understand, how we figured out the actual structure of benzene based on this evidence. So without further ado, let's go over the different evidence. First, we have our physical evidence. Now, our physical evidence starts with bond length. At the time, we were able to determine that the bond length of the benzene bond was somewhere around 139 picometers long. So each carbon to carbon bond within benzene was 139 picometers. However, we also knew at the time the carbon-carbon single bond had a distance or a length of 154 picometers, while the carbon-carbon double bond had a length of 133 picometers. Whoops. What we notice is that the length of the benzene bond fits right in between these two values. This shows us that this must have a hybrid structure between the single and double bond, as we learned that hybrid structures have intermediary properties. So we already know just from bond length that it could neither be a single or double bond, but somewhere in between. So we move on to our other form of physical evidence, which is bond angle. A weird thing about bonding is if we have carbon, double bond, single bond, and let's say this is oxygen and we have two hydrogens. These hydrogens would actually be less than 120 degrees, while the oxygen-hydrogen bonds would be greater than 120 degrees. That's because there is a larger electron density in the double bond, forcing a more repulsive force than just single bonds. However, in this hexagonal structure of hexene, if we look at a perfect hexagon, which that is not, give me a moment, maybe we can get my iPad to figure it out. So in a perfect hexagonal structure, the interior angles are 120 degrees. Each one is identical at 120 degrees. And if we look at our benzene structure up here, we would note that this would probably push further, making some angles a little wonky, and these would not be perfectly even. However, in benzene, the interior bond angles are 120 degrees interior in benzene. What that tells us is that each bond is identical, meaning that it cannot be double bonds and single bonds. So there's our physical evidence for the uh, resonance hybrid structure of benzene. But we have further evidence. We also have chemical. So when we do reactions with benzene, there's a lot of weird things that happen. And furthermore, when we do reactions with things made of carbon and hydrogen, some things are predictable. The first one is hydrogenation. Hydrogenation is a reaction of H2 and a carbon-carbon double bond complex. So something that has a carbon-carbon double bond. What ends up happening is that that carbon-carbon double bond plus a H2 will turn into a carbon-carbon single bond with the two H's, therefore taking that bond. So the H2 will break that bond right there. And so this is something that's possible, and it's possible to do with benzene. The thing is, hydrogenation has a predictable energy change. Uh, it's an energy loss, so energy is released. And regardless of the compound, it usually has a very set amount of energy that we know is going to come out per bond. So the weird thing with benzene is benzene, which in the original structure would have 3 double bonds and would therefore produce 3 times the energy of hydrogenation. If it's got 3 double bonds, for each double bond we break, we get that amount of energy, so 3 would be 3 times the energy. But this is where benzene differs and tells us chemically it must not have double bonds. Turns out that benzene releases far less energy than expected. What that tells us is that benzene starts benzene starts in a more stable configuration than if it had 3 carbon-carbon double bonds. Because it starts from a more stable configuration, it starts at a place of lower energy and therefore loses less. What was proposed and is true is that due to resonance hybrid structure, so that structure that we will be drawing in a little bit, uh, the molecule is more stable and has delocalized electrons. Kind of very similar to what we learned about graphite and graphene with those delocalized electrons. However, it's even more stable than that. One other chemical property we know, or chemical reaction that provides us evidence, so chemical evidence, is that we have this thing called addition reactions. With carbon-carbon double bonds, or carbon-carbon double bonds, are predictable. Again, very much like we saw with hydrogenation, an example of a carbon-carbon double bond addition reaction would probably be something like this. We take carbon bonded to carbon with 2 hydrogens, and we add bromine to it. So this is what you can do to test for presence of double bonds in a solution. If you take bromine and add it to a solution that contains carbon-carbon double bonds, that bromine gets added and we get a single bond. And this is a bit of organic chemistry that we're going to learn much, much later at the very end of this, but we need it for explaining benzene. Basically, we get this new solution where the bromine breaks this bond and adds itself to each carbon. This is why it's called an addition reaction. It's actually very similar to hydrogenation, but the difference between hydrogenation is that it deals with hydrogen, while addition can deal with pretty much anything. Now, the problem is benzene does something a little different. Benzene, and right now I'm just going to represent benzene as a B with a circle because I don't want to redraw it every time. If we look at one of its hydrogens and we add bromine to it, what we'll actually get is that bromine will replace the hydrogen, and that hydrogen will then bond with bromine to make HBr. So what actually happens is benzene does not undergo addition, it undergoes what we call substitution, thus providing evidence for no double bonds. No double bonds. We'll explain this in much further detail about 100 lessons later, but basically what this comes to is that the evidence points to resonance hybrid structures. So our actual diagram would look like this hexagon with our hydrogens coming out of it. And then we're going to use dotted lines where these double bonds would exist in the resonance structures. Now, what you may notice is this took forever to draw, so we actually just represent benzene much more simply as this hexagon with a circle in it. This also just generally means benzene. Now, before I end this lesson, I want to describe why we actually represent benzene like this with a circle other than just the fact that we're lazy. This circle actually represents the delocalized electrons in benzene. So what we can do is we can look at what actually happens. So in benzene, what ends up happening is the orbitals, which we're going to learn about sigma and pi bonds in our p and s orbitals, but you can tell from the shape that these are generally p orbitals. They actually all come together, and the p orbitals in one plane create a ring of electrons, and the p orbitals in the bottom plane create another ring of electrons, and we get these kind of like donut-shaped orbitals. And these hold the delocalized electrons from double bonds. So we're going to have 3 electrons in each of these, 1 electron from each double bond essentially, and they just kind of go in the circle and exist above and below the plane of the benzene molecule. So this is actually why we use the circle in our benzene shape, and the hexagon, of course, just represents the hexagonal shape of the carbon, 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 carbon bond. So with that said, I hope this helps you understand a little bit more about benzene, and have a great day.